All right, so now let's take a look at line integrals in space. So we're going to let C be a smooth curve in space. Given by x equals x of t, y equals y of t, z equals z of t, where t ranges from a to b. Or r of t is x of t I plus y of t j plus z of t k. Now let's suppose that f is a function of 3 variables, is continuous on some region containing this curve. Then we can also define a line integral of f along C. And this will be with respect to arc length. So the way this is defined is line integral of f along C is a limit as n approaches infinity, summation I equals 1 to n, f of xi star, yi star, zi star times delta si. So a very, very similar representation to what we saw earlier, which probably isn't that surprising. But we can think of this as the integral from a to b, f of x of t, y of t, z of t, times the square root of derivative of x with respect to t squared plus derivative y with respect to t squared plus derivative t with respect derivative z with respect to t squared dt. All right, so that's how we are going to go forward. And so with this next example, we'll take a look at a line integral. And this will be the line integral of y sine z along C, where C is a circular helix. Given by x equals cosine t, y equals sine t, and z equals t. And we're going to let t range from 0 to 2 pi in this case. All right, so we're going to need to know something about the derivatives of x, y, and z with respect to t, because we are going to have to, of course, figure out what this looks like. So let's go ahead and do that. If x is equal to cosine t, then the derivative of x with respect to t is a negative sine t. If y is equal to sine t, then the derivative of y with respect to t is cosine t. And then if z is equal to t, then derivative of z with respect to t is equal to 1. And in fact, I think what I'd like to do is just go ahead and figure out what this part is. And so we'll have square root of the sum of the squares of these derivatives. Is equal to the square root of square of negative sine t plus the square of cosine t plus 1 squared. But if you square the negative sine t, that's going to be sine squared t. You're adding cosine squared t, and we know sine squared t plus cosine squared t is equal to 1. So you're going to have 1 plus 1 squared, that's 1 plus 1 gives you 2. So it turns out that this part that we would see right here would actually just be the square root of 2 in this case. And so let's take a look at this given line integral. So we'll have line integral of y sine z along the circular helix. It's going to be the integral from 0 to 2 pi. And then we'll have y, which is sine t, times sine z, which is actually sine t, times, and then the ds is going to be this square root of the sum of the squares of the derivatives of x, y, and z with respect to t and dt. Well, that square root is square root of 2 here. So we'll have square root of 2 and dt finishing this out. Now, what this means is that we actually have, this is the same thing as the integral from 0 to 2 pi of root 2 times sine squared t dt. But we know what sine squared t looks like. We have an identity that says that it's equal to 1 minus cosine 2t divided by 2. And so, if you think about that, what you notice is that you got a square root of 2 over 2 times 1 minus cosine 2t. So we'll go ahead and take that root 2 over 2 outside. We'll have our 1 minus cosine 2t. It'll integrate from 0 to 2 pi. Now if we integrate 1, of course, we'll get t. And if we integrate a negative cosine 2t, we'll get a negative 1/2 sine 2t. So we got root 2 over 2 times t minus 1/2 sine 2t. We're taking that from t equals 0, t equals 2 pi. All right, so let's think about what's going to happen here. If we plug in 2 pi for t, we'll get a 2 pi here, and then we'll get a sine of 4 pi here, but sine 4 pi is equal to 0. If we plug in 0 for t, we'll get a 0 minus, and then sine of 0 is also 0. So it actually turns out that this just reduces down to a square root of 2 over 2 times 2 pi, but these 2's are going to reduce out. So final answer is going to be square root of 2 times pi. All right, so let's take a look at another example. And so in this example, we're going to evaluate the integral of y dx plus z dy plus x dz along C, where C consists of, well, it's going to consist of two different parts. Line segment C1, and that's going to go from the point 2, 0, 0 to the point 3, 4, 5. And this is going to be followed by the vertical line segment C2. And C2 is going to go from the point 3, 4, 5 to 3, 4, 0. All right, so we're going to figure out what this line integral is. Once again, you've got two different parts to this. You got the C1 and you got the C2. So we're going to think about C1 first. And let's keep in mind that we can write C1 as R of t is equal to, well, remember, this C1 is going from the point 2, 0, 0 to 3, 4, 5. So think of your R sub 0 as a vector with components 2, 0, and 0. Now that's going to get multiplied by 1 minus t. And then we'll have plus t times the vector with components 3, 4, and 5. Now, that means that R of t, well, if you take the 1 minus t times this vector, there we go, you'll have a 2 minus 2t, a 0 and a 0. And then here you'll have a 3t, 4t, and a 5t. Which means that our R of t is going to have a first component. 2 minus 2t plus 3t gives you a 2 plus t, sorry, or t plus 2. And then you'll have a 0 plus 4t as your second component, and a 0 plus 5t as your third component. And don't forget that when we set up this vector value function like this, t is ranging from 0 to 1. And so that means that we would have x equals t plus 2. We would have y is equal to 4t, and we would have z is equal to 5t. So this is really nice from the standpoint of when I go back to this part here, I can replace the y with 4t, the z with 5t, and the x with t plus 2. But I also need to know what's going on with dx, dy, and dz. But that's pretty easy, because if x is equal t plus 2, that just means dx is equal to dt. If y is equal to 4t, that means dy is 4 dt. And if z is 5t, that means that dz is equal to 5 dt. So I got all the pieces I'm going to need to put in here to transform everything in terms of t. So let's see how that all plays out. Well, take the line integral along C1, y dx plus c dy plus x dz. That's going to be the same thing as the integral from 0 to 1. The y is 4t. The dx is dt. Plus z, which is 5t. Times dy, which is a 4 dt, plus x, which is t plus 2, times dz, which is 5 dt. And so if you think about what all is going on here, you got a 4t, got a 5t times 4 gives you 20t. You have a 5t plus 10 here. And you'll notice you have some like terms. So 4t plus 20t plus 5t is going to give you a 29t, but a 29t plus 10. Now, integrate with respect to t. You got your 29 halves t squared plus 10t. We will plug in 1 for t and then subtract what we got when we plug in 0 for t. And that's going to give us 29 halves plus 10, because of course plugging in 0 for t is just going to give us 0. We know 10 is the same thing as 20 over 2. Add 29 over 2, you get 49 over 2 as your result. So that's what you get when you integrate this along C1. But that's only part of the story, because remember, C consists of that line segment from 200 to 345, followed by the vertical line segment from 345 to 340. And so now we have to think about what's going on with C2. So we can write C2 as R of t 1 minus t times, and now we'll have 3, 4, 5 as the R0 vector, and then plus t times, and we'll have 3, 4, 0 as the R1 vector. Now you don't really have to do it this way necessarily, but it does work. So we'll have R of t. You'll have 1 minus t times 3 gives you a 3 minus 3t. 1 minus t times 4 gives you a 4 minus 4t. And 1 minus t times 5 gives you a 5 minus 5t. And so when you take a look at multiplying t by this vector, you get a 3t, a 4t, and a 0. Now, we take a look at R of t. 3 minus 3t plus 3t is going to give us 3. Take a look at 4 minus 4t plus 4t, that gives you 4. And then 5 minus 5t plus 0 gives you a 5 minus 5t. And we have 0 less than or equal to t less than or equal to 1. Now this is what I was mentioning not too long ago, is you didn't necessarily have to do it this way, because if you take a look at the starting point and the ending point here along this line segment, you're noticing that x is maintaining a value of 3, y is maintaining a value of 4. So then basically you just need a parameterization that's going to take your z value from 5 to 0. And so 5 minus 5t certainly does that as you let t range from 0 to 1. So now, if you take a look at x, y, and z, you've got x equals 3, y equals 4, z equals 5 minus 5t, and of course, t ranges from 0 to 1. I need to know something about dx, dy, and dz, however. But if x is equal to 3, dx is going to be 0. If y is equal to 4, dy is going to equal 0. And if z is equal to 5 minus 5t, then dz is going to be negative 5 dt. So when we take a look at the line integral of this along C2, still have the integral from 0 to 1, but our y is going to be 4, our dx is going to be 0, plus z, which is 5 minus 5t, dy, which is 0, plus x, which is 3, times dz, which is a -5 dt, which this all zeroes out here. That means we're going to have a integral from 0 to 1 of -15 dt. So, not too bad. Not too bad at all. Because when you integrate, you get a -15t. Plug in 1 for t, subtract what you get when you plug in 0 for t. So you'll get a -15 times 1, -15, minus 0, that gives you your -15. Now, at this point, we've got to put it all together. Take the line integral along C of y dx plus z dy plus x dz. That's the same as the line integral of this thing along C1 plus line integral of the same thing along C2. Well, the line integral along C1 was 49/2. And the line integral along C2 is a -15. Take the 49/2 minus 15, that's 49/2 minus 30/2, which gives you 19/2 as your final answer. All right, so there's one last part to this section. Here we're going to be taking a look at line integrals of vector fields. So one of the things we learned in chapter 12 is that if you have a constant force that we're going to denote with vector F, and you want to move an object from one point to another in space, we can call this a displacement vector D, then the work done by the force in moving the object from this initial point here to this terminal point here is given to us by the dot product of F and D. So once again, this is something we learned back in chapter 12. But now what we're going to do is use this information to try to figure out something a little bit more. So let's suppose that you have some sort of continuous force field on R3. So we're going to let F equal Pi plus Qj plus Rk. We're going to let that be a continuous force field on R3. And so what we're going to want to do is figure out the work done by this force in moving a particle along a smooth curve C. And so if you want to take a look at a picture, that's probably not a bad idea. So we got our axes like so. And who knows, maybe this curve is going to look something like this. So we're going to have our p sub 0 here, a p sub n right there. And of course, there's going to be some sort of parameter t that we can have ranging from a to b. And when t is equal to a, that would generate this point, p sub 0 on the curve. When t is equal to b, that would generate the point p sub n on the curve. And we can partition that interval, that t interval from a to b, into subintervals of equal width, just like we did at the beginning of the section. And that's going to give us a bunch of different points. And so you might have maybe some sort of p sub I here. Maybe this is actually p sub I minus 1. Let's do that. Maybe it's p sub I minus 1. Maybe this is a p sub I. And what we're going to want to do, once again, is try to figure out the work done by this force in moving our particle along this smooth curve C. So what we'll do is try to figure out an estimate for the amount of work done in moving the particle from this point to that point Because if we can get an estimate for the amount of work done in moving the particle from this point to this point, we could do that for every pair of consecutive points along this curve, and then sum up all those work estimates to get an estimate for the total amount of work done in moving the particle along the curve from p sub 0 to p sub n. And so we think about how exactly that would work. Well, once again, you got this subarc that goes from p sub I minus 1 to p sub I along this curve C. And what we're going to do is we're going to take a representative point. Should not be a shock to anyone. We're going to be taking a representative point. And let's say we take this as our representative point. And that's going to be some sort of p sub I star. So p sub I star, which is going to have coordinates xi star, yi star, and zi star. All right, so that's our representative point from subarc I. Now, once again, you got to keep in mind that this point actually corresponds to some sort of ti star that's in our I t subinterval. So where do we go from here? Well, keep in mind that if you take a look at the length of that subarc, that's going to be delta s sub I. So let's go ahead and write that down just as a note. So delta s sub I is the length of subarc I. But let's take a look at this representative point for a moment. You might remember the unit tangent vector from several chapters ago as well. So here's what we're going to do. We're going to take this unit tangent vector. That unit tangent vector is going to be a t of t sub I star. Because the unit tangent vector is going to be based on our parameter t, and once again, I just mentioned that this point is going to correspond to some sort of t sub I star in our t interval. Now, if you want to figure out the estimate for the amount of work done in moving the particle from this point to that point, then we're going to have to go back to that dot product of force dot displacement. So you might have some sort of force vector, and maybe that force vector at this location, maybe it looks something like this. Or maybe it'll look like something when I get a marker that works. That would be a novelty. So let's say that we have a force vector that looks like this. So that's going to be our f of xi star, yi star, zi star. So if you think about an estimate for the amount of work done in moving this particle from this point to that point, what's going to happen is the displacement is going to be estimated by the unit vector times this delta SI. So this unit tangent vector times delta SI, once again, you're basically, what you're doing is you're taking the displacement vector to have magnitude that's approximately delta SI, because that's the amount of distance that a particle would be moving from here to there, and the direction would be approximately the unit tangent vector evaluated at Ti star. And so we think about our displacement vector as this unit tangent vector evaluated Ti star times delta SI. Now, that gets dotted with our force vector. And so we think about, well, what is that actually going to give us? Well, the work along subarc I, which I'm going to call W sub I, would approximately be equal to f of xi star, yi star, zi star, dotted with t of ti star times times delta SI. Now, you could also think of perhaps this T of Ti star as T of Xi star, comma Yi star, comma Zi star. And if you were to take a look at summing this sort of thing as I ranges from 1 to n, then you would get an estimate for the amount of work it takes in moving the particle from PO or P sub 0 all the way to P sub n. And so, total work done. Total work done, we'll call it W. And moving the particle from P sub 0 to P sub n, we would think of as summation I equals 1 to n f of Xi star, comma Yi star, comma Zi star, dotted with T little Ti star, delta Si. And so we could write this as W is approximately summation I equals 1 to n f of Xi star, comma Yi star, comma Zi star, dotted with T of Xi star, comma Yi star, comma Zi star, because after all, what is this tangent vector based on? It's based on this representative point we chose. And then you got your delta Si. So this kind of looks like a Riemann sum. Kind of looks like one. If we were to take the limit as n approaches infinity of this summation, that would give us a line integral along C of f xyz dotted with T of xyz with respect to S. Now, we could think of this a little bit differently. In fact, there are a few forms that we could actually revert to here. So, if you think about the fact that this curve could be represented by some sort of R of x of t, comma y of t, comma z of t, then what you could say is that W is equal to the integral from a to b of f of R of t dotted with, well, think about this unit tangent vector. This unit tangent vector, if you go back to the definition, this is the same thing as R prime of t over the magnitude of R prime of t. And then we take a look at the ds, and one thing I mentioned a bit earlier in the section is that ds is the same thing as the magnitude of R prime of t dt. So the magnitude of R prime here and the magnitude of R prime here would reduce out, and that would give us that W is the integral from a to b of f of R of t dotted with R prime of t dt. And oftentimes we abbreviate this and the way we abbreviate it is the integral f dot dr along C. So this oftentimes is represented with this notation. So we'll go back to our definition. We'll let F be a continuous vector field defined on a smooth curve C. F is a continuous vector field defined on a smooth curve C. And this smooth curve C is going to be given by a vector function R of t. Where t ranges from A to B. Then the line integral of f along C is this thing right here. But remember, this is going to be the same thing as the integral from a to b, f of r of t divided with r prime of t dt. Which is also the same thing as f dot t ds. So this is going to be the line integral along C, f dot t ds. So a few representations here. But what we're going to do is we're going to take a look at an example where we find the work done by a certain force field and moving a particle along, in this case it'll be a quarter circle. So we're going to find the work done. By the force field f of xy equals x squared I minus xyj. You're moving a particle along a quarter circle. And this quarter circle is given to us by r of t is equal to cosine ti plus sine tj. And t is going to range from 0 to pi over 2. So we're going to need to figure out what the work done is, and that's going to be the line integral of f along C, which is our integral from a to b of f of r of t dot r prime of t dt. So let's go ahead and figure out what f of r of t is. Now when you're thinking about f of r of t, basically what's happening is the cosine t is an x of t, sine of t is a y of t. So x is going to get replaced with cosine t, y is going to get replaced with sine of t. So everywhere you see x here, replacing it with cosine t. Okay, so x squared I, you'll have cosine squared t I. Then minus xyj, well the y is going to get replaced with sine t. So we'll have a cosine t, sine t, j. And remember, r prime we got by taking the derivatives of the component functions of r. So we'll have a negative sine ti plus cosine t j. All right. Now, according to the formula we see here, we're going to need to take the dot product of these two. And so we're going to have f of r of t dotted with r prime of t. I'm going to write just a little different form here. So cosine squared t is going to be our first component of f of r of t. Negative cosine t sine t will be our second component. And we'll dot that with r prime of t. So we'll have a negative sine t as the first component, cosine t as the second component. And when we work this through, you'll have a cosine squared t times a negative sine t. That's a negative cosine squared t sine t. And then we'll add the product of the second components here. But you multiply these second components together, you get another negative cosine squared t sine t. So So you put this together, and that gives you a negative 2 cosine squared t sine t. So this is what we're going to need to integrate from 0 to pi over 2 to get the work done. Let's go ahead and do that. So W is the integral from 0 to pi over 2 of a negative 2 cosine squared t sine t dt. But to work this out, we're going to need to do a substitution. So we'll let u equal cosine t, which means du is a negative sine t dt. Now, this works out very, very well, because we'll have a negative 2u squared here. Sine t dt would be the same thing as negative du, but if we were to think about it, you really do have a 2 times u squared, and then the negative sine t dt is the du. So what happens here is you get integral. We'll worry about the limits of integration in just a moment. Cosine squared t is a u squared. Got a 2 out in front. And the negative sine t dt is your du. All right. So now, limits of integration, we'll take these t values, plug them into the substitution equation. Plug in 0 over t, u is cosine 0, which is 1. And if you plug in pi over 2 for t, you get u is cosine pi over 2, which is 0. And so w is going to be 2/3 u cubed. When we integrate the 2u squared, that's what we get. And then top limit of integration is 0, bottom limit is 1. But if you plug in 0 for u, 2/3 times 0 cubed gives you 0. Subtract what you get when you plug in 1 for u, and that'll be subtracting 2/3, so the work done is negative 2/3. All right. Now, there's one final note that I'd like to put up here. So we're going to let F be a vector field on R3. And that vector field is going to be given to us by F equals Pi plus Qj plus Rk. Now, let's keep in mind that when we write down this Pi plus Qj plus Rk, just remember that all three of P, Q, and R are functions of x, y, and z. So if we were to take a look at this line integral of f along c, remember we saw that that's equal to integral from a to b f of r of t dot with r prime of t dt. But remember what f is. F is this Pi plus Qj plus Rk. And we're dotting that with r prime of t dt. Now if you think about what r prime is, the components are going to be x prime of t, y prime of t, and z prime of t. But if we're looking at truly f of r of t, then remember that pi, remember that's the same thing as p of x, y, z, I. But if you're plugging in r of t to f, that means that what you're really getting is a p of x of t, y of t, z of t times I. Okay. So what that means is that this is going to be the same thing as the integral from a to b. Well, when you got to take your dot product, then what you're going to get, you got to multiply the p times x prime, you got to multiply the q times y prime, you got to multiply the r times z prime. Now, I'm not going to have nearly enough room to write this down on one line, so just please bear with me on that. But what we're actually going to get here is the integral from a to b. We'll have our p x of t, comma y of t, comma z of t times x prime of t, plus, and we do something similar for the q, so we'll have a plus q of x of t, comma y of t, comma z of t times y prime of t, plus r of x of t, comma y of t, comma z of t times z prime of t dt. So that's what we get when we take the dot product of the pi plus qj plus rk together with this r prime of t. But if you think about it, this is the same thing as line integral along C of p of x, y, z dx plus q of x, y, z dy plus r of x, y, z dz. Because this thing, put it together with the dt. What's x prime of t dt? Oh, that's right. That's the same thing as dx, isn't it? Right. So if you have x equals x of t, dx is x prime of t dt. Well, that's what you're seeing right here. X prime of t dt, same thing as dx. So you got your p of x, y, z dx. Similar fashion, y prime of t dt is the same thing as dy, and z prime of t dt is the same thing as dz. And so this can be written as the line integral along C of p of x, y, z dx plus q of x, y, z dy plus r of x, y, z and dz. So that means line integral of f along C is the line integral of p dx plus q dy plus r dz along C. It's just that f is going to be pi plus qj plus rk. So if you think about one of the earlier examples that we saw, you may recall in this example we had the line integral along C, y dx plus z dy plus x dz. But if you think about it, this has the same form as what we're seeing here, with p equals y, q equals z, and r equals x. So we could have thought of this as line integral of f along C, where f is equal to yi plus zj plus xk. Oops. There we go. Plus zj plus x. Okay, there we go. And with that, 16.2 is finally finished. And after all this, recommended exercises, I have 3 of them I'd like for you to take a look at. 1, 13, and 19.